My name is Yoon, and I'm from the Applied Science Group at Microsoft. So today I'm going to present our recent work, HapSense, soft haptic input-output device. So this work is done with my colleagues Siyuan, Shantanu, Flávio, and Jim Holbery. So haptic systems have been widely adapted to efficiently transfer and convey information. However, the most haptic feedback system still relies on the actuator like shown in this picture, which are rigid and hard, which are composed of the rigid and the hard components. And this limits the applicability in applying the haptic system in the highly flexible system and prevent the potential in seamless integration. To this end, many researches have been done on the soft input and output devices, but still there are limited in the system that can provide the dual functionality like input and output, and also for the soft output devices, they usually require very high operating voltage in kilovolt level. So in this work, we are proposing the PVDF-based soft input-output devices. So this one is composed of the ferroelectric electroactive polymer, which can provide the concurrent vibrotactile actuation with the force sensing. So as haptic feedback becomes widely incorporated in various devices and interfaces, researchers have coordinated the sensing capability with the haptic feedback. Still, it requires a discrete hardware and the discrete sensors to compose the system. So this results in a complicated system design, as well as requires us large like physical space for embedding these systems. And many soft input and output devices have been recently explored, and with the good body conformability and good mechanical durability. Still, input-output devices are solely providing either sensing or actuation, and there is not much device that can provide concurrent vibrotactile actuation with the force sensing. And in material science field, researchers have demonstrated dielectric elastomer actuators with the sensing capability called the self-sensing actuators. So in addition, the multilayer electroactive polymer actuators using PVDF have proposed. But currently even in material science field, there's a limited hardware which can concurrently provide the vibrotactile actuation with the force sensing feedback with the uninterrupted dual functionalities. So this is one of our main contributions to this work. So thus our main goal in this study is to come up with a soft input-output device enabling uninterrupted sensing and actuation. So to achieve this goal, we consider the following factors. First, our device should support the flexibility and the softness, which we aim to build our device such that it can come with the low profile, conformable form factor. Secondly, we consider several use case scenarios which can utilize the input and output interaction utilizing the vibrotactile feedback and the force sensing. And lastly, we carefully selected our fabrication method to support non-material scientists like myself. So let's look at more detail of the fabrication. So to support fabrication for practitioners and non-material researchers, we chose process and assembly methods that do not require the customized and high-cost process equipment. Also, we tried our best to maintain the assembly and fabrication process in the room temperature, so the fabricators do not have to consistently working among different temperature settings. So let's look at our overall fabrication process. So with either fabricated or purchased PVDF film, we apply the conductive silver electrode with the manual screen printing process. And here we use the ink consists of the stretchable silver flake. And after screening printing process, we cure this substrate at 100 degrees Celsius for 1 hour. Then we then attach the laser pattern acrylic adhesive film, which can be assembled in room temperature. With many multiple units, repeating units, we can actually vertically stack these units to different number of layers to finalize our design. And at the end, we can make an interconnection with the electrical external devices by providing the conductive epoxy to the through holes. And our fabrication method can create a minimum device dimension of 5 by 5 by 0.7 millimeter, and it has a minimum bending radii of 2 millimeter, and the bending stiffness of the proposed devices was measured to be 15 megapascal. And unlike the previous soft sensor fabrication, we do not require the industrial grade pad printer or the pre-processed stretching. So with the fabricated soft input and output devices, we enable the uninterrupted sensing and actuation with our customized portable hardware with the multi-mode input-output system. So these allow us to remove the high power, huge power supply that often requires to actuate the soft actuator. And we also, using the different modes in system, we optimize the power consumption for concurrent sensing and actuation. So let's look at the basic working principle. So HapSense can generate vibrotactile feedback with a time-varying driving voltage across adjacent electrodes. And working as an actuator, PVDF piezoelectric polymer film deform once the electrical charges are induced. And to work as a force sensor, dielectric geometric changes caused by external force resulting in capacitance change, which change the driving voltage profile, and we can easily detect this driving voltage profile change by using the envelope detector. So let's look at this. So here's the working prototype. So as you can see, we are concurrently driving 300 volts driving voltage, which provides a vibrotactile actuation, while we can also process the force sensing concurrently. So our system can simultaneously actuate sense with the two different modes, called the hybrid and the sensing omni mode. So here we propose these two modes to optimize the power consumption. For example, there's a case where we only want to measure the force sensing without driving the actuations. So in this case, HapSense can act as a sole contact force sensor with a significantly lower driving voltage. And we measure the force level by monitoring the actual voltage across the HapSense using the envelope detector. So here, unlike the previous piezoelectric method, we did not use the charge generated from the piezoelectric effect. So based on the different modes, like hybrid mode and the sensing omni modes, the driving voltage can be adjusted because we did not utilize the piezoelectric effect. And supporting both modes using the same hardware lowers the system cost, and the system complexity. So here we designed the battery-operated low-power board capable of generating sufficient driving voltage up to 350 volts with arbitrary waveform. And board can be powered by the single 3.7 volts LiPo battery. And currently the power consumption is 300 to 600 milliwatt, but with one more iteration, we already reduced it down to more than half of the power consumption. And we foresee that the further optimization with hardware iteration can be further reduce the power consumption. So with the functional prototype, we carried out evaluation of the device both as a sensor and an actuator. So first, we confirmed the physical displacement of HapSense during actuation using the laser vibrometer. And as the driving voltage is induced, we can easily observe the physical deformation of the whole device. And these measurements are aligned with the result that we got from the MEMS analysis device, which we also characterize output force and displacement. So you can refer our paper for more detail. So sensor performance was also characterized using a customized system setup. And as you can see, when we apply the pressure was increased from 0 to 12 kilopascal, we see modest increase. And from 12 kilopascal to 45 kilopascal, we see the subsequent increase in the capacitance. But for pressure larger than 45 kilopascal, we did not observe apparent capacity change. So we think the range of the pressure we can measure is from 0 to 45 kilopascal. And before going for the main user studies, we actually investigate to confirm the base performance of the HapSense as an actuator. And here we try to find out the minimum driving voltage threshold for the tactile sensation. So we use the prototype with the 20 PVDF layers, and we use the random double staircase method to find out the minimum tactile threshold. And the result verified that the thresholds among users are far below than the breakdown voltage of the actuator, which is 400 volts. And from the result, it is recommended to keep the driving voltage at least more than 150 volt to deliver perceptible stimulations. And in our main study, we carried out user study to validate functionalities while exploring design guidelines for the proposed device. First, we look at the force sensing performance of proposed device on different operation modes and the different mounting surfaces. Also, we look at the user preferred input force to trigger an actuation event. So here we measure the force sensing on the touch and press, and the two different mounting surfaces, the hard acrylic plate and on the user's hand, user's wrist. And we also testing on the hybrid and sensing omnimodes to see whether that has any effect on the performance. So from the result, one exemplary force distribution pattern from the single user, we found that there is a pattern that people exert more forces while interacting on soft devices. This is because we observed that people tend to exert force until they feel the force from their fingertip as on the mounting body. So this was aligned with our observation. And second thing is we look at the SNR for the sensing and for the touch and press. And we observe lower SNR for when we're mounting on the wrist surface because it's expected because it's the electric field coupling between HapSense and the human body. And we also observed that the lower SNR on the hybrid mode, which you assume it is due to the electrical and mechanical noise from device when there's an actuation exists. But still, those odd SNR exhibit more than 23 decibels, so we think it's robust for the sensing touch and press. And for the second task, we actuate our device with a different triggering force. And previously, a study using the rigid piezo ceramic buttons was carried out to identify user preference for the vibration. We further extend our explore user preference for operating soft haptic input and output devices. And participants were asked to rank among 5 different force triggering thresholds, which was found in our preliminary experiment, and on 2 different mounting surfaces. And as you can see, for the users prefer light triggering force when the device was mounted on the rigid surface, and people prefer higher triggering force when it is mounted on the human body. So this implicates the design guidelines that the triggering force feedback should be carefully selected among different mounting surfaces for our device. So here are the few example applications that can be done with the concurrent vibrotactile actuation with the force sensing. So this one showcases the straightforward approach of making existing object as an interactive input and output device. Here we just attaching our device onto the sirenage, so we can use it for training the user with the right pressure and training for the right pressure. So here it can be done because we use the single system to provide the vibrotactile actuation and the force sensing in a same node. The second thing is multiple units of our device can be configured to provide richer information. Here we just exemplify 2x2 interactive nodes, which can be connected to the different applications to control, as well as getting the notification from those kind of applications. And our device can be also easily wrapped around the human skins to provide wearable input with the confidence. So upon successful tap or press gesture, HapSense can vary vibrotactile feedback to confirm the input control. So it can easily increase the confidence when you are actually processing the inputs. And HapSense can be embedded onto various soft enclosure with the low profile and soft form factor. Here, our prototype can enable localized sensing and actuation on back of the device to support the rich user experience such as the gaming and the streaming. So there are the limitation and future work is still underway. So first is that we have not conducted a comprehensive investigation to characterize the system durability over a large number of cycles. So potential remedies will be applying the durable protective layers on or below the device. And secondly, there are still rooms to improve the performance of the device where we can optimize actuation resonance frequency by varying devices' dimensions. And lastly, we can add additional multimodal input-output functionalities by we can add the output functionalities such as we can actuate device in audible frequencies to play sound. And we can also utilize the pyroelectricity nature of this device to do the temperature sensing. Yeah, thank you, and I'd like to answer any questions.
Another really nice talk. A question right here.
Thanks for your talk. I would like to ask you the fundamental difference of this work from a lot of flexible electronics research from, for example, John Rogers or Jenambauer, Sang-Hee Kim, or Someya Takao.
Yeah, so from those works, they are having a lot of work from those soft material society, material science society, and there are many devices which can actuate in the very high kilovoltage, or even there are some devices that can operate in low voltage with a large number of the layers. But the fundamental difference here is that we enable the system that can actually provide the concurrent vibrotactile actuation with the sensing in the same system. So those devices, when you usually look at it, there is usually different equipments are hooked up into the same device, and they don't process the actuation and the force sensing in the same sensing frame. Yeah.
I have a question. I'm trying to get my head around kind of the mechanism you're using to sense force. Is there any potential to sense shear, especially in some of the applications that you demonstrated? It could be interesting to do isometric pushing around in different directions. Is this technology going to lend itself to that at all?
So at current moment, we are just using this as a single sensing node at this moment, but it can be done with the more complicated design in a way that because of the different layers, we can design different layers with the different shapes to increase the number of the sensing nodes. But I'm not sure how much resolution we can obtain with that approach at this moment. Yep.
For future investigation.
Yep.
Okay. Well, if there's no more questions, then we'll have a final round of applause for all of our speakers. These were fantastic talks. And I am very inspired.